Did I just start?
Yeah.
Okay. So
it says monomer double dimer model
with long-range interactions.
Yeah, no, but it's
Our long-range order in the monomer double dimer model with long-range interactions.
Yeah, please.
So this was a joint project together with Lorenzo Tacci in Rome and Wei Wu in Shanghai, and was mainly done during my research stay in Rome. So at this point, I want to thank Lorenzo for hosting me and my supervisor, Volker Beetz, for giving me the opportunity to travel around. And I think most of the people here are not familiar with statistical mechanical models. So I will take it a bit light, and I will give you in the first 5 minutes a bit of an outlook what I plan to do, such that you can maybe follow a bit better. So the first 5 minutes are not rigorous at all. We just draw some pictures and I give you the outline. So everything, I think, starts with the dimer model. And what's the dimer model? It's somehow the study of perfect matchings. So let me draw a picture. We take a subgraph and we want a random subgraph such that each vertex has exactly degree 1. So for example, a configuration could look like this. And this is an interesting object in combinatorics, but also for us as mathematicians, right? And what could we do? We could superimpose this now by a second dimer configuration. And if I superimpose this with a second color, then what we get is this loop structure. And what we then want to do is studying this loop structure. Because what this relates to is a permutation model. So if I draw this graph again, and then when we look at this as permutations, this could, for example, be a configuration which look like this, right? And the question for permutations would be now a bit more natural if we freeze a certain number of points at random, right? Because if we want to study permutations, what we want is we want that we also include the identity. So what we want to include are this kind of points. And therefore, we want to study the monomer double dimer model. And the monomer double dimer model is a similar model, just that we have a random intensity of monomers. Let's say here's a monomer, and then we again have this kind of dimer configurations. We superimpose, and for example, we have a long loop here and 2 monomers here, and this corresponds to this permutation. And that's an interesting object in probability, right? But it's also interesting for mathematical physicists or physicists, because by this Feynman-Katz representation, this corresponds to a Bose-Einstein condensation, or the study of these long loops corresponds to Bose-Einstein condensation. So it's interesting also for physicists to study this model. And a natural extension would be now to consider this model with long-range jumps. So instead of only allowing nearest neighbors, we want to extend somehow long jumps for these dimers, because these Bose-Gars where this is studied is with also these long-range jumps. So that is what we do. And now let's be a bit more precise. So we start with a simple finite graph G with vertex set E and edge set E. And this is simple and finite. And the edge set E is such that we have xy, such that there's a positive weight function, wxy, which is positive. And for this weight function, you consider as examples e to the minus the distance x minus y in the 1 norm. Or if you want to think of nearest neighbors, then just take the indicator and then x minus y in the 1 norm to be 1, right? Then we just recover the normal weights. And like I said, we have this monomer activity. So this is a positive number, and it's called monomer activity. Sorry? You can think of a subgraph on ZD. We mainly work on this, but you can. It's the graph norm. Or this is the, which one? This one is the one norm. So the graph norm. So, okay, let's draw one more picture. How configuration looks like. So we have some monomers. Let's say we have a monomer here, we have a monomer here, dimer here, maybe one here and one here, and then a red superposition, here one and here. So this is like our configuration could look like. And now let's build the probability space. So we have white dimers M1 and we have red dimers M2. So what we need is that these white and red dimers are elements of 0, 1 number of E cross 0, 1 E. And now we have this condition, what you can see here. Either we have a red and a white one at a node, or we have no dimer at all at the node. So this is the condition that the local time at x of M1 is the same as the local time of M2. And this is an element of 0, 1 for all x. So this is our probability space. And this local time is just given by the sum over all vertices such that y and x is an edge. And then we sum over the number of dimers on it. And now, given the configuration, the probability measure e.g. rho w of m, this is given by the product over the weight of the monomers, so 1 minus nx of m1, and then the product over xy is an edge, and then wxy mxy1 plus mxy2. So this is not a probability measure anymore. So what we have to do is we have to divide by the partition function such that we get a probability measure again. And what this probability measure does is, okay, if there is a dimer at the node, right, then this is 1, so this becomes 0, so this weight kicks in. And if there is no monomer, then we get 0 here, so we get just the monomer weight, because then this one is also 0. And what happens if we restrict ourselves to nearest neighbor weights, then we just recover the normal monomer double dimer model again. So then this reads as as rho to the number of monomers divided by the partition function. Okay. And like I said, we are interested in studying these loops. So an important object is Lx of m, and this is the loop touching x. And what we are also interested in is the absolute f value of this. And this is the number of dimers in the loop. And a question at this point is, what is the expected size? Size of the loop touching the origin. And if you are in the setting where you have no monomer activity and you have nearest neighbor weights, and your dimension is greater than 2, then the answer is that this scales with the volume of the box where you look at, and this was a result from Lorenzo Tacci and Alexandra Wittmann in 2023, I think. And okay, the next question is a bit more about the...
Can I ask a question? I don't see where the long range comes in.
And I don't talk about long... oh, sorry. The long range is because we have these long range edges, right?
Yeah.
Yeah.
But how do I see that in your definition? So is that hidden in,
this is hidden
your
in
NX?
I mean, it's in the probability measure, right? Because...
No, so it sits in the fact that your edges could be longer, but they are controlled by W-axis? I don't know, because for example, I'm confused about this arrow that you'd say, well, e to the minus x and then this indicator, but that's nearest neighbor.
That's nearest neighbor, right? Yeah.
And so your W-axis are some function of x.
Yeah, exactly.
And you might change that so that...
Exactly. We look at different rates because the method we work with different rates. But I think the easiest rate you should have in mind is exponential, or if you want to think about something else,
otherwise it's not
polynomial.
Local enough.
Yeah. Sorry?
The word geometry in the set.
Yeah.
Or it's length one.
Yeah. I mean, and the underlying graph, right? That's also a bit of geometry you have.
What is long about the edge?
Sorry?
What is long range about the edges?
So because we not only consider nearest neighbor edges, so that's why we say long range.
So then what's the geometry of the vertex set V?
I think V is just your underlying, okay, it's we look mainly at set D, so these points, and then connecting, then you have the different edge set. Okay? Okay.
So this is somehow hidden in the way you choose your WX.
Yeah.
Which you have to choose, and the nearest neighbor case is the easiest one, and that's not long range. Okay.
Yeah. Okay.
Because that's because of that function e to the negative, the graph norm of x minus y. I'm guessing that the smaller that is, the quote unquote, the longer the edges for us.
No.
I mean,
if you take, for example, exponential weights, then it's more unlikely that you have these long jumps, right? So it's somehow an integrability condition you have. Okay, and now let's talk a bit about okay, I see. About long-range order. And so let's start a bit. What happens if we disturb the graph? So I draw again a picture, and what I then like to do is that I say I choose 2 points, exactly 2 points. Let's say this is y and this is x. And these are now white monomers. So what white monomers mean is that I can still place a red dimer on it. So let's perform a configuration, which look, for example, like this. So you see, we can still attach the red monomer at the white dimer. And what we then get is we get a walk inside this model with a lot of loops. And we want to question ourselves, how does this impact compared to only have these loops? And this is somehow related to long-range order. And this question comes from physics, because think of a magnet. And what you want to understand is, if you have a spin somewhere which points up, does it inflect? Does this spin still correlate to a spin to a node which is far away, right? And this is somehow encoded by these paths or loops. And if this quantity stays positive, then we say this model has long-range order, so this phenomenon in physics, and we say these quantities are positively correlated to each other. So what we want to study is therefore the 2-point function. And the 2-point function, like I said, is we have one of these walks, only loops, divided by the normal partition function, which is only loops. So if we define it rigorously, then we have GG rho W of X and Y, and this is the G rho W XY divided by the partition function. And this object is just the sum over white dimers, red dimers, in the special probability space where we fix this node XY to be a white dimer, and then the normal density set V without XY, rho 1 minus n set M1, and then product UV element the edges, and then the weight UV MUV1 plus MUV2. So in this, studying this object is studying long-range order. So what we would be interested in is question how, what is the asymptotic? Is the asymptotic of this two-point function G as X, Y goes to infinity? Or is there an asymptotic? And before we tackle this question, I maybe speak a bit again about the dimer model. So a dimer configuration is a subset D of the edges such that each vertex has precisely vertex of V and D, has degree 1, like I said, and we call the G the configuration space. And then this is the two-point function. Sorry, I was a bit, it's sorry? What is the expected size of the loop touching the origin? Okay, you define a special vertex to be the origin. So you can take any vertex you like, but yeah.
What is norm X minus Y1?
So you can think of the underlying, so what I like to think about is, think of your graph as connected via nearest neighbor edges. And then the distance from X to Y is just you count the smallest path between.
We're defining this for like WX5 for the, for just like, yeah, so it's like we have like a different edge set that we start out with, and then we get this other edge set over here, this WX5 0.
Yeah, but you want for this question, you want to graph them. You want to know how far these are really away, not only in jump size.
Right. So yeah, I'm guessing like we have some other edge set, but now we've modified it.
Yeah. So what the probability measure reads like is this is just the product over the edges, and then the weight divided by the partition function. So, and then we have also a monomer correlation function. And this monomer correlation function is you fix 2 points, X and Y, and these 2 points you freeze. And then you perform a dimer configuration on the complement of these 2 points. And then what the monomer correlation function reads like is it's sum over configurations where you have put out these 2 points. So it's dg minus xy. And then the product over the weight, UV, divided by just the normal partition function. And why I want to talk about this is, which is a bit unnatural at first point, is if you take rho equal to 0, then the 2-point function at 0, this is just the monomer correlation function. And this is just for calculational reasons, since if we look at ZG0W, then what we get is just this overlap of 2 dimer configurations. So this is just the partition function of the dimer squared. And if we look at ZG0W of xy, then this is just Z of xy from the dimer model times the partition function from the dimer model. And now we divide by each other and recover the monomer correlation function. And another reason why I want to talk about this is because for the monomer correlation function, if you are on a planar graph and and you have nearest neighbor weights, then there are a lot of answers to this question how this 2-point function behaves. And the shortcut is that it behaves, it decays polynomially by works from Castellin, Fisher, Kenyon, and Bida. So yeah, so this is a bit the opposite of what we do. In this case, the 2-point function decays polynomially. And what I want to talk about is what happens if we are non-planar. So we take ZD, for example, the greater or equal to 3, and then this 2-point function will not decay. So let's come to our results. We work on the torus, which is that B, L, Z, D, and Z. Okay, and for our case, consider the 2 example weights. The one is exponential, e to the minus gamma, x minus y in the 1 norm. And the second one, which is polynomial, so wxy is cy p, d minus y in the p norm to the power of gamma, and the norm is 1 or 2. And these gamma should be greater than d and less than 2d for integrability reasons. And then one theorem we have is that suppose we have the weights 1 or 2. D is greater or equal than 3. And then there exists rho 0, such that for all rho between 0 and rho 0, there exists a positive constant C1, such that the lim_inf of the sum over all 2-point functions from 0 to x divided by the volume of the torus, this stays positive. So what this result says is that at each volume, at each scale, you have macroscopic dependencies of these walks. And what this says for Bose-Einstein condensation, on a really low scale, because this level is this model is just an approximation, that you have at each box size a macroscopic scale of bosons which are in the same state. Or if you think of a magnet, then you have at each size of the volume a lot of particles which point in the same direction. And if we have in addition that the weight is 0 if we have even jumps, then we get also that we have a second constant which is positive, such that 1 over the volume of the expected size of the loop is positive and is also bounded from above by this constant. So we also know about the size of the loop. But therefore, we need this condition. And a result which complements this is Mermin-Wagner-like theorem, which we also have, which says is, suppose the random walk with jump distribution W is recurrent, then for any row greater or equal to 0, the lim inf, or the lim of the expectation of the loop containing the 0 divided by the volume, this is 0. And the limit L to infinity of 1 over the volume of the sum of 2-point functions, this will also be 0. So this is with a complementary result to the first one. And let me use the last 2 minutes to explain how one gets such a result. The thing is that the system or this model is not monotone in the parameter. And at some point, you obviously need some sort of inequality, right? So the normal inequalities you get from monotonicity or something like FKG will not work. And therefore, we use with a method which is called reflection positivity. And this is also the reason why we play on the torus. So what we do is we have this torus, then we have a reflection plane in the middle, and then we reflect each vertex to the other side. And what you then get is an inequality which says that if you have this torus and you have a loop, let's say here, and a loop, let's say here, and then the squared of this probability is less or equal than if you would symmetrize the system. So you have the one loop here and here, so it's kind of symmetric, times the probability where you have the loop down here and down here. And then we play with this inequality and get these results. And I think that's all I want to say. Thank you.
Thank you. Questions?
Like in the edge set we defined in the edge set that we've defined that way,
I assume that we're also counting like self loops, and those will have weight.
No,
one.
because the graph is.
So simple. Okay,
Yeah.
so those just we won't count those. So those
Yeah.
will have weight 1 equals 0, I guess, for
Yeah.
us then. And like if they were not like connected in the initial like edge set, then they would have like that weight. I mean that norm would be infinity, and that's why we would have weight 0 there, so we wouldn't count it in the edge set
exactly.
effectively. Right. Thank you.
Okay.
No, I just wanted to understand how to interpret that 2-point function. Like what is happening and how is that related to the loops touching the origin? So if
The
you could
2-point function?
Yeah, the 2-point function, like how is that, like how should I understand it? Like
Okay.
what is it representing?
Good question. It's the 2-point function is, okay, we fix these 2 points, right? And we say we put a white monomer there. And what happens is that you generate these walks inside these loops. And now you want to ask the question, how expensive is it to generate these walks compared to only have loops? Because you divide by the normal partition function, right? So the question is always, how expensive is it to generate these walks? So this is the way you should think about it. And expensive means how strong are they correlated? Are they a lot of walks between it? Are these walks expensive because they also depend on the weight of the edges, right? And if this 2-point function stays positive, then it's not that expensive to generate these walks. And therefore, what this means for the system is that these 2 points always remember that they are connected in a way to each other. So if you think in physics, in this spin sense, let's say you have a spin which points up at one point, and then this connection, this line says the 2 nodes always remember that the spin goes up at some point. So because it's cheap this walk is cheap, so it's cheap to remember how these things are arranged. Does this answer your question? Thank you.
Okay, thank you.